All right, so this is the second class. Got started last time and showed you on the first project where you set up your virtual machine. And a couple students came to my help session last night for help with their virtual machines, and I applaud that. It's definitely great. I'm available Monday through Friday at 7:30. You can connect to this Twitch, and then I'll turn on the Zoom, and you can come in there and share your screen, and I can help you with anything. You got to get a virtual machine going, or you won't have any fun. And by the way, a bunch of people are doing great work. Like, these people have done the first project, but a bunch of people have started raging ahead. In fact, these people have done like half of the whole class, which is great, So I applaud it. Feel free to work ahead, pull ahead on things. You could go ahead on the quizzes too. I got all the quizzes up for almost the whole class in Canvas. So feel free to charge ahead. Anyway, today we're going to talk about C. So let me bring in the slides for that. All right, and I think I mentioned in this class, I'm mentioning a few of my classes that's come up, why C exists. In the early days, mainframes had a separate language for each hardware vendor. They were not compatible. And you'd have IBM, buy an IBM mainframe, and it would come with a bunch of phone books, thick documents teaching you the IBM language and so on. And they decided to improve that by inventing the language, the operating system called Unix, which would be the unifying operating system, so all those machines would be the same. And in order to do that, they had to write a language called C to write Unix in. And then all they'd have to do is write a C compiler for each hardware vendor. And that would be different, but that's all you'd have to do. After you'd done that, you could then write code that ran on Unix, and the same code would run on all that hardware, and then you could have the internet, where all those machines could talk to each other. So that's how it all started, and so C was an essential part of creating a uniform operating system that cut across different hardware platforms so we could have the internet, along with many other things like software that we could then distribute and run on many different machines. So we'll talk about the basics of C programming here. And the thing about C is still popular in its derivatives like C++ and C#, because C is very efficient and very fast. So if you write code in C and then compile it, you get something like Microsoft Office. And when you distribute it, it's very difficult for people to reverse engineer and modify. It's small and fast, and these advantages have made it extremely popular. But the disadvantage is it has a whole series of really severe security problems. And for more than 20 years, actually a lot more than that, it started in 79. So it's more than 40 years we've been using C. Nobody's ever found a way to stop them from keeping on making the same mistakes over and over. So as I mentioned, Rust is becoming more and more popular as an alternative to C. But anyway, it's real important to understand C, especially if you want to understand Linux and Unix. So it's a high-level programming language. It's very old, so it doesn't have object-oriented programming. That came in much later. And by the way, it doesn't have strings, lists, or dictionaries like Python does. All those are later abstractions that didn't exist in the very early days. It runs very efficiently because it's very close to assembly code. You're controlling the hardware very directly. So if you compare it to Python, in C, you have to have a main function. In Python, you often do. You don't necessarily have to, depending on how you do it. But the point is, this is your tip. You have to have a main function in C. That's where the program starts. And then you can have print statements and return, and that's it. You have to include libraries specifically. So this one, you had to include math and standard I/O, so you could do a square root, and so you could have print statements. All right. So in Python, you can have multi-line comments with 3 apostrophes and a pound. In C, you start your comment with /* and end it with */, or you can use // for single-line comments, so that's a difference. In Python, you use import to import libraries. In C, you use include. All right. Here's a really big important thing. White space matters in Python. If you have a block of code, you define something here, you have to indent all these lines with a certain number of spaces or tabs, and it must be consistent. And the indentation indicates how much of the following statements are included in this block starting after a colon. That took me a long time to learn because I started from C. And the fundamental rule about C is that white space does not matter at all. Before the compiler compiles anything, it just strips out the white space. You don't need carriage returns, spaces, tabs, or anything. None of them mean anything. They're just there to make it look prettier to the developer. So in order to, if you have a statement which sets up a condition that applies to a block of statements after it, you use curly braces. And that's why you have to end every line with a semicolon. because there isn't any out here in Python. You end a line with a carriage return, and that indicate. But in here, carriage returns mean nothing. So a semicolon ends a statement, and curly braces indicate blocks of code. In C, all right. So you don't need main in Python, but in C you need the main function, and it's typically an integer function, so it returns an integer value, and it might have arguments, but if it doesn't, then you put void in here if you want to be strictly correct. You can also just leave it empty, and most of the time the compiler won't complain about that, but this is considered a little more perfect to do it this way. So if there's no error, your function will return 0. If it returns something non-zero, that's considered an error code. All right, in Python, each statement's on a separate line. In C, you end them with a semicolon. And for output, print is formatted string, and it's printf in C, and you must include format specifiers, placeholders. %f indicates floating point, and there are a bunch of others. So indentation, like I say, matters in C. It doesn't have any, it matters in Python, but it doesn't matter in C. You just have to have whatever style makes the code readable for you. And the printf statement does not print a new line character at the end. You'll have to explicitly include \n to go to the next line. When you're importing libraries in C, you have to do it in multi-line comments. You don't, though the comments are entirely optional. The import is just this here, include math_h. These comments up here, you don't need to have them at all. The include statement is what brings in the library. And that has to be exactly like this. #include and angle brackets, and then the name of the library .h to bring in the header. Yeah, it's not inside the comment. By the way, that's real important. Putting anything that matters inside a comment is a horrible practice, and that comes from HTML. HTML is the worst programming language on earth. It is horrible. You actually mix several languages together, like PHP, HTML, and JavaScript all in the same file. All the purists in computer science were horrified when they started doing that, with good reason. Insane programming languages, you don't only have one language per file. And comments are just comments, and there's nothing that matters in the comments. So C is that way. You could totally remove all the comments, and it wouldn't affect the running of the code at all. The comments in the white space are removed before the compiler hits it. They're just there for the developer. A real important question, and a good question, like I say. Unfortunately, HTML has created the situation where you might expect stuff inside the comments to matter, which is a horrible idea. Anyway, all right. So that's good. All right, so you got a main function. Its return type is int. All right. All right, by convention, it should return 0. If you don't put in the return 0, it doesn't crash or anything. All right, your Python interpreter is like a virtual machine it runs on. When you run Python, Python is typically an interpreted language, not a compiled language. So you define code, and when you run it, it translates it line by line into executable code. Just like, say, the bash command shell. You execute a command, you print enter, it turns that into assembly machine code and runs it. It's line by line. And you don't typically compile it and create a separate executable. Therefore, it runs a lot slower. It's not intended for things that require high performance. But in C, you write the code, save it in a text file, then you compile it, and the compiler turns it into a binary executable, which you then run. And the point of this is smaller, and it's also very difficult to reverse engineer this binary executable back to that, especially if you compile it by stripping out all strings, and therefore this is favored by professional developers making commercial programs like Microsoft Office, where you want to distribute something that is small and fast, and you want to make it difficult for people to pirate your work by getting back to the source code. And of course, it's also popular for malware developers who want to distribute something that will execute on machines doing something malicious like stealing your passwords. And again, they try to make it difficult for you to read this code to understand what it is. So that's the game. So you compile it. If you just do gcc hello.c, it will compile by default into a.out. Therefore, I always specify where it should go with gcc -o, but if you don't do that, it'll put it in a.out. Now on Debian, and this is true of most operating systems these days, most people are not developers, and they're not ever going to write any code, so the default installations of most operating systems do not include a development environment. They expect you to run programs written by somebody else, like games and office utilities and browsers and stuff, but they don't expect you to develop anything. And indeed, if you have a running server that's providing a service to people, like a game server or a social network server. You don't want people compiling code on that machine because that would probably be a bad guy compiling code. So really, only a small number of machines should have developer tools, so they're not there by default. So this is what you have to do on your Debian machine to put in the essential building environment so you can write code. So let me just do this in case you haven't seen it. Let me get my live machine here, clear. All right. So this is my SSH shell into a running Debian virtual machine, which is running, in this case, on genuine Intel hardware. I'm using my older Mac now that has an Intel processor. So if I do uname -a, you'll see I have Debian Linux, and it's running AMD 64. So I have a 64-bit Intel-compatible AMD processor. By the way, it's probably one of the ones with that microcode vulnerability I was just talking about in the news. But anyway, there's my processor. So I've made this program. I can cat hello.c. And there it is. I include math and standard I/O. I have the declaration of the main function. Then I have a print that'll just print hello world. And this print will print square root of 4. And this is the literal text. And here's the placeholder. So it takes square root of 4 and print it there where the placeholder is, and then return 0. So to compile that, I can do gcc hello.c, and that creates a.out, which does that. Normally, I would not do it that way. Normally, I would do this -o hello. This is the standard thing you do. I don't want everything going into the same executable named a.out. That's sort of silly. Instead, I specify where it should go. So now it's going to create an executable called hello. And if I do ls-l, then you'll see here's my hello.c program, and here's the compiled hello program. The hello.c is only 140 bytes. The compiled program is 16 kilobytes or so. And that's got all the sections it needs to be an executable, so it turns green in this environment. And you can tell by the permissions here, the X means execute permission. So this is executable. These are readable and writable by the owner, but they're not executable because they're just text files. So that's the first little bit of developing in C. And so you got variables, of course. Your variables have a scope and a type. The scope determines what part of the program you can use the variable in. And the type determines what kind of data it stores. So here, the curly brace determines the scope. So if you open some block of code with a curly brace and declare variables inside here, they only exist until you leave the curly brace. That's the region of code that rather in scope. The commands that happen outside those curly braces won't know the values of these variables. So I define an integer, and then a couple more integers, then a character variable can hold one letter, then a floating point variable, a double precision floating point variable, and I can now do math on them. You can assign integers to your integer variables and do math on them. You can put a single character in a letter. Now, this is something that is really messed up. And again, I learned this about C, and it was real hard for me to unlearn when I moved to modern languages like Python. In C, characters are just integers. So a letter equals A just is going to be the numerical code for capital A, which is 65. 41 in hexadecimal, and so you can just do math on it, letter plus 1. Now, in an intelligent, sane language like Python, you wouldn't be able to add a number to a letter. That doesn't make any sense. You could append a character number to a letter and end up with 2 letters in a string, but you can totally do it in C. And after you get used to this is also the way Fortran worked, I think, so I was used to this for decades. It was very hard for me to learn modern programming where characters are actually Unicode characters and strings are actually series of characters. They aren't byte arrays. But in C, they're just a byte array is all a string is. So a letter is A, that means it's 64, and integer 65, and you can add 1 to it, now it's 66. Now it's going to be interpreted as B if you treat it as a character. You can have pi, you can do a calculation, so on, and you can do a modulus calculation. All right, so here's various types. There's an integer value. This is a double value, a floating point value. Here's the character H. If you interpret it as a character, it's an H. If you were to interpret it as a number, it would be 104, the ASCII value of H. So this is a really disturbing thing, and this is going to be part of what leads to the serious vulnerabilities of C is that strings are just a series of bytes. So you'll see we're going to exploit this pretty soon in the projects. All right, so you got a lot of numeric types. You have character, which is 1 byte, which is the same as an integer, except integers are typically 4 bytes. You typically want them to carry more than just like 0 to 255. So a character is a 1 byte integer, and you got long and float and double for floating point and integer variables. And so this is an assigned int variables. Default, you can specify unsigned if you want, and then it'll interpret it from 0 up to the maximum, which is about 4 billion, instead of going from like minus 2 billion to plus 2 billion, which is what you get otherwise in a 4-byte integer. You can find the size of the types. The size is not absolutely fixed by the C specification, so you might different programs might choose different sizes for the variables, so you can find out what the size of function. How big is an int? How big is a short? This is usually what you'll find. 4 bytes for an int, 2 bytes for a short. So you can do all the usual math, add, subtract, multiply, divide, modulus. You can assign variables to value, and you can combine, instead of putting I equals I plus 1, you can have I plus equals 1. Same thing we do it in Python, just a little shorthand to change the value of a variable. And you have increment and decrement. These are pretty common across many languages. And you can also put the plus plus on the left, which means increment it first before you use it. If you put it on the right, it means use it and then increment it. So that's kind of cute. Although I've never used that, but you know, it's there if you want to. By the way, this is a general rule of programming. They often allow you to do very confusing things, like C has a way to make an if statement with nothing but punctuation marks, just a question mark and then parentheses, and the first clause is what happens if it's true, and the second clause is what happens if it's false, something like that. And it's impossible to read. I never use it. I highly encourage you not to get clever. Don't use bafflingly cute ways to write code. It's much better to write clear code that you can read. So people can understand it, and believe me, so you can understand it yourself. Many, many times I go back to code I've written, and I can't understand what I'm doing. So when I first learned this stuff, I tried to do all the cute things, and as I got older and more mature, I said, you know, I'm just going to make everything as easy to understand as possible. I'm not trying to prove I'm smart anymore. I'm trying to actually just be successful and reliable, which is a different kind of goal. Anyway, let's try Kahoot. I should have these open someplace. Yeah, here they are. Okay. So this is just an optional online game you can play to get a few extra points. If you're in the top 3, you get 3 points. In case there's anybody here that wasn't in the last class and don't know what's going on here. This is the only thing you can do that's worth points that you can't do if you don't attend class live. And all this stuff is being recorded. There'll be videos of it up for anybody who doesn't want to attend class live for whatever reason. Kahoots 2, 4. All right, I'll wait another measure or two. All right, I guess we got everybody that's coming. All right, so which feature does C lack? It doesn't have object-oriented code. That didn't come out until decades later. All right, so how do you denote a block of code? Yep, curly braces. It's indentation in Python, curly braces in C. All right, what indicates the end of a statement? Semicolon, have to have one after each statement. All right, how large is an int typically? Yep, 4 bytes, so it can go from -2 billion to 2 billion, which is enough for most purposes. All right. All right, good. I see you people are using your real name, which is a good policy. Some students use fake names in the Kahoots, and that's okay too, but you do have to tell me your real name so you get your points. In this case, they all look like real names, so there shouldn't be any trouble figuring out who you are. Anyway, all right, so then you got input and output, which is printf and scanf. So you have to include stdio. The standard I/O libraries are not included by default. You have to put them in there. And so in Python, you can just do print. In C, you have to include standard io.h, and then you use printf. And printf has a format specifier, and then it has what you're going to print. Now here they put a literal string here to print with the %s specifier, which is kind of screwy. I've never done that. But this is what you usually do. You can put an immediate value here to print, or you can put a variable here to print, which is haven't given you. Anyway, that's the point. Notice the way you print it all out, and anything starting with a % is a placeholder. So this holds room for a string. This holds room for a decimal value. \t is a tab character, and \n is a new line. So you get used to those things. And a lot of other languages use similar abbreviations for that. So %g is also a placeholder for a float. There must be some difference between %f and %g. I don't know what it is. I've always used %f. %d is decimal, and %s is for string. %c is for a single character. Those are common ones. We'll get to format string vulnerabilities a little later. You can take over a machine through the format string. It's one of the many flaws in C. We'll get to that. But anyway, the character is a number, what I've been complaining about. You can define a character variable, ch, then set it equal to capital A, and then you can print the same thing out twice, once as a decimal and once as a character. So now 65 is the value of A, 99 is the value of lowercase c, and once you get used to this, it's sort of insane and stupid. This is, by the way, a really bad idea. It's a really old idea, like I say, from 1979. There are a bunch of reasons why this is a bad idea. One of the big ones is there are only 256 possible values of a single byte. And in ASCII, you only use the first 128 of them. 127, really. So that's not enough characters. That's enough characters for English. Uppercase letters, lowercase letters, numbers, and some punctuation marks. But the world is bigger than English. You got Hebrew and Arabic and Chinese and Japanese, and you want to represent all those languages too. So this is a really bad system for encoding characters. And that's why the modern world uses UTF-8 Unicode, where each character can be up to 4 bytes long, and now you can encode all those important languages. And now a string is a series of characters, and each character can have a variable length. That's how it goes in modern language like Go or Python. But C is a very primitive old language, and it only handles English. It doesn't even handle small variations of English like umlauts and backticks and stuff that you find in like French and Germany. So it's it's very limited in that regard. It's very powerful, though, and you need to learn it. It's very useful, very close to assembler. But as far as actually making modern applications that would run in multiple languages and stuff, these strings are really a weak spot of C. It really doesn't have the variable support you need to handle modern multi-language programming. Anyway, scanf reads data in, so you can print, and then you scanf, you give it the format specifier of how to interpret the data that comes in, and this is something that always takes me a while to get used to. You have ampersand num. Now you defined an integer variable num, and that means there is a pointer which points to the address in memory where that number is stored, and then there's a value stored there, which will be 4 bytes long. And this ampersand is the address operator. So you do not pass into scanf the variable you're reading. You pass into it a pointer to the variable you're reading. So it will read this data, interpret it as a decimal number, and write that number into this address. You must remember the ampersand or it won't work. And that is where you begin to get the really confusing part of C, which is understanding pointers and pointer dereferencing. That's the difficult, confusing feature, but it's really important because that gets you down to how assembly code really works. So it's really at the heart of this class, and it's part of why C is hard to write. But some of C is hard to write for stupid reasons, which leads to vulnerabilities. This part of C is hard to write because it really reflects the real way the hardware works, and we need to learn that. That's what we're here for, to use C as a window into understanding how the hardware really works, and these pointers are a big part of it. All right, so that's what the ampersand operator is. So it gives you an address pointing to that variable. So now we're going to read two values, ampersand x and ampersand pi. This is an integer, and that's floating point. So the first one will be interpreted as a decimal, and the next one as g. Now notice I didn't put a carriage return here or space between them or anything, because all that matters is the format specifiers for input, and this means you can use any kind of white space to separate these, spaces, tabs, or new lines. The input parser in C is quite primitive and easy to confuse. It's not really that good at reading in data, but it'll handle simple cases. All right, and so now you got conditionals and loops. I enter the first number, I enter the second number. Now, if number 1 is greater than number 2, then print that. Otherwise, print the other one's biggest, that sort of thing. This is how you make an if statement. You have if, then you have a condition that's either true or false. Then you have a block of code in curly braces. And then you have else, and you have another block of code. That's very much the way almost every other language would do it. The only difference, of course, in Python is you use colons and indentations to indicate which block of code is in each block. Here you use these curly braces. And that's called a Boolean value. Now, other languages actually have Boolean values that are just true or false. C doesn't. Boolean values are integers. And the integer is true if it's anything other than 0. It's false if it's 0. So that's another sort of shorthand. And boy, I remember I learned this, and I thought every language would be that way too. Just like I thought every language uses 1 byte for character. These became absolute axioms in my mind, and it was very difficult for me to grasp programming languages where that wasn't true after years of programming in C and such languages. So you got equality. If you use a single equal sign, this is a very common mistake, you're performing assignment. So if I equals 1, that's going to take 1 and assign it to I. That's not comparing them, it's double equals to C, does I equal 1. That's inequality, less than or equal, the usual stuff you'd find in any language. And so here's y less than 0, y not equal to 0, okay, sort of thing. And notice here, if x greater than equal y, then y equals x. This is assignment, not comparison. This is comparison, not assignment. Yeah, I was just wondering, the due dates on the project since the Canvas. The due dates are, they don't really matter because the automated scoring system doesn't punish you for being late. So the due dates are just there to guide you. Don't worry if you're late. I just recommend doing it at that time to stay caught up. It's not like you have to get it done on the due date or it's no good. My automated scoring system will give you points no matter when you turn them in. But if everybody starts putting everything off till the last week, then I'll have to implement some kind of punishment for being late. But that's not happening. So good, a very important question. All right, so here's logical negation. Then if condition is not true, and here logical and logical or, so you can say x greater than 10 and y greater than x, greater than equal x, that sort of thing. That's how you combine them. They compound conditionals, they call it. And again, that's pretty much the way every other language does it. So you can have a while loop. While this condition is true, it will do this. So you have to do something inside here that will eventually make that condition false, or it'll run forever. So I'll val less than num, do something, and then make val bigger, so eventually it'll get too big. That's the sort of thing. You can also have a do and put a while at the end if you want. This way, it will always do it at least once before it hits the while. In this case, it may never do it at all. If the condition is false in the first place, it will never do it at all. All right. And you have for loops. These have been around forever. First kind of loop I ever learned in a long extinct language called BASIC. So you have your starting condition, I equals 0. You have the condition which determines when you're going to be done. As long as this condition is true, the loop will run. And this is where you have the code that's executed every time the loop runs, typically to increment it. So I starts at 0. As long as it's less than num, you'll execute the loop, and after each execution, you'll do this to increment it. And then you can do whatever you want in here. All right. And then you have functions, of course, so you can have structured code. You don't have to write spaghetti code with goto the way I used to in Fortran. So here we're going to have a max function. You just define it the way you define your main function. The variable type here determines what kind of answer it's going to give, what kind of return value it's going to give. Typically, you use an integer, and a 0 means it worked, and another number means there was an error, but it can be anything you want. And it's going to have, this one is going to return the maximum of these two numbers. So it's going to take x and y as integers. It's going to figure out which one is bigger and then return the bigger of the two. So that's fine. Notice, by the way, this bigger variable only exists within this function. It's defined within the scope here, the curly brace and the closing curly brace. Outside there, that bigger variable will not exist, and you can't use it. But, as we're going to see, that's another one of the many security flaws in C. You can end up using something after it's fallen out of scope, and that's called a dangling pointer, or use after free. That can happen, and then you can write to areas of memory you're not supposed to write to, and that's one of the many memory corruption vulnerabilities you can use to take over machines if you make mistakes in your C code. All right, so the stack is where most of this stuff is stored. When you enter this function, it defines the local variable bigger, so you start in the main function. Then when you call bigger, you pass it the parameters here. You say return bigger, res equals max of a, b. So it's going to call max of a and b, so it's going to take these two variables from the main function and put them on the stack, and then enter res, which enter max. That's going to retrieve them. It's going to create a stack frame to store local variables. It's going to make a copy of those input variables x and y and work with them, calculate this bigger variable, and then we'll return the bigger. So there's several things to notice here. One is, when you're inside this function, this stack frame is created, it's temporarily storing these variables. When you return, this stack function this stack area is freed, not used anymore. It is not cleaned. It is just no longer in use, and the old data is just left there. And another thing is, if you were to change the values of x or y inside this function, they would only change in this stack frame temporarily, and when you return, it would not change the variables at this end. You can pass it a pointer, and then when it changes the variable, it'll actually be changing the variable in the other function. But if you pass it by value this way, then it passes a copy of those values into here, and there is no way to send them back. So the only thing that comes back is the thing you return. Anyway, we'll play with the stack quite a bit in the projects. And then you have arrays and strings. Let's see, schedule section due dates, shown on the left. Yeah, there are due dates in there, that's right. But like I say, I'm not enforcing them. I'm not taking away points if you're late. All right, so in Python you can make an array, just append things. You have this is called a Python list, really, is what you use. But in C, you only have arrays. You don't have lists. In Python, lists can contain items of different sizes or different types, and C doesn't have anything like that. In C, you define an array. So you have integers, you give it a name, and you have enough room to store 10 integers. That's it. They all have to be the same size of data. So you have enough room for 10 integers. So now you can set the value of all those. This will set them to something, and off you go. So that's important. And this is the problem This is the most common, most serious problem everybody knows about C is buffer overflow errors, because you have these buffers and there is no real record of how big the buffer is, and there's no mark at the end of the buffer, so it will cheerfully let you read and write off the end of the buffer. So here you've got a test function that is just going to take a pointer to an array. This is passing in a pointer. So you define array 5, and when you call it, it's going to pass the number, the name of the array, which is a pointer to the start of the array. So now, when you set a3 equal to 8 in this function, it's going to actually change it in the calling function. This is how you can make a function that will change values up here. You don't pass it the raw variable, you pass it the pointer to the variable. All right. And so strings have to end with a null byte. That is the convention. In retrospect, this is probably a bad idea. Pascal had a different system. In Pascal, the first byte determines the length of the string, which can go from 0 to 255, and then you have that many bytes. Therefore, Pascal wouldn't have such a severe buffer overflow problem as C. But C does. So if I define a string up here, I define character string 1 of 10, string 2, 10 long. I can set the first element of string 1, which is called 0h, then I, then a null byte. So that's going to be a 2-letter string high, and then a null byte to terminate it. And so if I calculate the length of it, it's going to show me 2. Now I can do stir copy, which will copy string 1 into string 2. And then print that, it will print high. So this works fine. The problem is, now I could string copy hello into string 2. Now it's going to be 5 characters long. The problem, stir copy is one of a whole series of functions that is dangerous and leads to buffer overflows, because you could copy a long string into a short string that doesn't have room to store it, and C will not put up an error message or warn you or not do that. It will just take as many characters as it has to and copy them starting where this one starts, with wise disregard for running off the end. So, and there are data structures, although I don't remember ever using them in C. You can make structures like this with several variables with one name. So you can define a structure, student 1, student 2, and each one of them has these various types of data in a structure, and this means the same thing it would in any other language. You have a block of data. So you have a bunch of char variables here for the integer. You have a 4-byte integer for this, then you have a floating point value here, and looks like another integer here. You know, that's all one structure with one name. All right, so let's try another Kahoot, which is 1b. Oh, now I understand that comment in there. Yeah, I put the due dates on my main web page. Yeah. I think it does actually say them in Canvas, but it doesn't matter. My web page is the main part, is how I organize the class. I only use Canvas for discussions and quizzes, really. It's a good quiz engine, but I don't really have much use for the other features. I did write my own quiz engine for some of my earlier classes, but it wasn't as good as Canvas. So, all right. All right. So how do you bring library code into C? pound include. All right. All right. How do you indicate a normal counting number, like 1, 2, or 3? Yep, %D for decimal. All right. All right. How do you read an integer x from the keyboard? Yep, you need this one with the placeholder to tell it how to interpret it and the address operator, ampersand, to refer to the address of that variable. That's it. All right, so what data type is not present in C? It doesn't have Booleans. By the way, I would like to say it doesn't have strings. It has something it calls strings, but they are really not much like an intuitive grasp of a string, and that's what leads to a world of problems. Anyway, all right. All right, 3 for Emmanuel. And Adrian. All right. Good. All right. I'm going to stop this recording.